We close this first lecture of Chapter 4 on equilibrium with a discussion of the biological standard state. We indicated earlier in this lecture that the sign of the standard reaction Gibbs energy change, delta RG standard, can only accurately predict the spontaneity of a chemical reaction when the value of Q is sufficiently close to 1. That is, when the composition of the reaction is sufficiently close to that described by the standard conditions. When we refer to the standard state in chemistry, that is, when we refer to the chemical standard state, we imply that activities of all solutes in solution refer to the standard molarity of 1 mole per liter. Similarly, the activities of all gases refer to the standard pressure of 1 bar. Since activities are calculated with reference to a standard concentration or standard pressure, the value of an activity depends on the choice of the standard state. Similarly, the reaction quotient also depends on the choice of a standard state. One can easily see that a standard molarity of 1 mole per liter does not describe well the pH conditions in most living organisms. Except for digestive processes, the pH relevant to many biochemical processes is slightly over 7. This obviously implies that the relevant proton molarity in most biochemical processes is about 10 to the minus 7 times lower than the chemical standard value of 1 molar. Similarly, the oxygen pressure relevant to most biochemical processes is 0.2 atmosphere, the partial pressure of oxygen in air. The relevant carbon dioxide pressure is 0.003 atmosphere, the partial pressure of CO2 in air. As a consequence, scientists who do thermodynamic calculations in the field of life science have chosen a different set of standards, called the biological or biochemical standards, to describe proton concentration, oxygen and carbon dioxide partial pressures. The biological standard state symbolism uses a superscript 0 followed by a prime or a superscript plus within a 0. The biological standard state is defined as follows. For solutes other than protons in ideal dilute solutions, the biological standard state is still the molar concentration, and the activity is therefore defined by the ratio of molarity over molar concentration. For protons in ideal dilute solutions, the biological standard state is a molarity of 10 to the minus 7 moles per liter, and the activity is the proton molarity divided by 10 to the minus 7 molar. For oxygen gas, the biological standard state is defined by the biological standard pressure of 0.2 atmosphere. The activity of oxygen gas is the ratio of the partial pressure of oxygen in atmospheres divided by 0.2 atmospheres. For carbon dioxide gas, the biological standard state is defined by the biological standard pressure of 0.003 atmosphere. The activity of CO2 is the ratio of the partial pressure of CO2 in atmosphere divided by 0.003 atmosphere. For all other gases, the biological standard pressure is still 1 bar. I must emphasize that using the biological standard state has important consequences for applications of the relationship between delta RG standard, and Q. As will be shown on the next slide, if a chemical reaction involves either protons in aqueous solution, oxygen or carbon dioxide gases, the activities for these species will be different when you use the chemical standard state or the biological standard state. Proton activities will differ by 10 to the power 7, while oxygen activities will differ by a factor of 4, and carbon dioxide activities will differ by a factor of over 300. For a reactive mixture of a given composition, the existence of different activities, when using different standards, imply that the reaction quotient will also have different values depending on the standard state used in these calculations. If you recall that delta Rg is the maximum reversible work that can be done as a result of a spontaneous reaction, then you can understand why such work, and therefore delta Rg, must have a value independent of the choice of the standard state used in the calculation of delta Rg from delta Rg standard NQ. This implies that the difference between the values of Q calculated using chemical and biological standard states must be compensated by the values of delta Rg standard calculated using chemical and biological standard states. On the next slide, we show how to relate delta Rg biological standard to delta Rg chemical standard for a chemical reaction involving protons. The main result to remember from this slide is that different standard states give rise, for the same species in a given reactive mixture, to different activities, hence different reaction quotients. Use of the biological standard state is designed to yield activities for protons, oxygen, and carbon dioxide that are close to 1, hence to define a delta Rg standard whose values are closer to delta Rg values than what is afforded by the chemical standard state.